Hi everyone. Welcome all of you to my presentation on application of multilane microscopic modeling to measure mobility and safety consequences of mixed traffic in freeway weaving section. I am Mudasser Seraj, working on my PhD in transportation engineering under the Totoni's supervision. Since we have very little time for this presentation, I'll jump right into it. The research question that I'm trying to answer through this part of my research is how can the mobility and safety of varying traffic states in a multi-lane weaving section be influenced by the shared presence of automaton-driven and human-driven vehicles. In this premise, the twofold objective of this descriptive research includes contriving a comprehensive and realistic modeling framework of mixed traffic, and quantifying and clarifying the causal connection between presence of automated vehicles in traffic with paradigm shift in mobility and safety benchmarks for a weaving section. Now I'll provide a brief overview of the microscopic modeling framework that's been developed for this study. Model predictive control based motion algorithm is chosen for modeling both human and automaton driven vehicles. Subject vehicles longitudinal and lateral control is implemented by computing the current traffic state from the input data and predicting its future pattern. In each time step, the subject vehicle is provided with two sets of data, vehicle status memory and environmental inputs. With those inputs, the subject vehicle decides between longitudinal and lateral controls to update the vehicle status. To validate the proposed traffic model, numerous simulations were run having only human-driven vehicles for varying infrared and microscopic parameters were recorded. The capacity of the simulated section was identified as 2088 vehicle per hour per lane. Comparing the obtained capacity with the highway capacity manual recommended capacity showed that the capacity value falls under the curve for lane changing vehicle ratio of 0.1. The model-generated fundamental diagram exhibited the capacity at 23.81 vehicle per kilometer per lane density level that falls under level of service E for freeway weaving section, which is the stated level of service for capacity according to highway capacity manual. The mobility consequences resulting from mixed traffic movement was measured considering two key parameters, maximum throughput and average speed of traffic. As portrayed on top left figure, the variation of maximum throughput was nonlinear. Maximum detriment in throughput was experienced at 10% automated vehicle share, and maximum gain was attained at 65%. As observed in top right figure, the average speed of traffic resulting from various infrareds were highly dispersed at lower automated vehicle shares. However, with the increasing automated vehicle shares, the resultant average speed became increasingly concentrated, shifting towards the speed limit. Safety critical time to collision events were detected from simulated scenarios with maximum throughput and then translated into relatable safety parameters such as potential conflict events and the crash risk index. Left figure showed the pattern of potential conflict events at varying traffic states. Spatial distribution of corresponding conflict events are plotted in these figures. O and Kim proposed a methodology to estimate the crash risk index from TTC values of all the vehicles, which was used in the analyzed roadway segments. The overall crash risk index showed nonlinear downward trend. To attain a balanced mobility benefit, both the average travel time and average travel distances were leveraged to calculate mobility scores. Safety scores were achieved by measuring the reduction of crash risk index from the base case. A neural network is developed with inflow rates and automated vehicle shares as input and corresponding mobility and safety scores as output. The finalized model was then applied to obtain scaled mobility and safety scores for specific inflow rates and automated vehicle shares in the weaving section. Furthermore, the model imported optimal automated vehicle share information to achieve maximum combined mobility and safety benefits for the specified inflow rate. This information would be critical for traffic operation and management authorities to impose controls enabling inflow rates and automated vehicle shares to attain more efficient flow and safer traffic movement through weaving sections. Finally, in conclusion, the analysis results reveal that low automated vehicle shares and high inflow rates have an adverse impact on mobility. Also, safety features of traffic in weaving sections were found to be exponentially associated with automated vehicle shares. And finally, the simulation results were assembled to develop an assistive application for traffic operation and management authorities that can aid traffic state evaluation from both mobility and safety perspective. That's all from me today. Thank you for your time and attention. If you have any question, feel free to reach out to me and I'll be happy to answer your questions.